Okay, thank you very much. And thank you very much to the organizers for inviting me. And they suggested that I put a few questions in. So I took it literally and start with a question. So what is a sample? And but you will see what I mean by that. So a longer title could be, then a more accurate, how to express what is a sample of a real valued random variable. So I'll talk only about real valued random variables, okay? And so what will come out that we want it to be a multiplicative and linear functional, okay? And then probably if we put some topology on random variables, we'd like it to be continuous probably. So and then we'll see what problems arise with that. Okay. And so the whole thing is how to cast this idea of random variables and observations and expectation also into a mathematical framework, and how to formalize what it is, and then to see how can we represent it. Because different representations lead then to different computational ways of dealing with it, okay? Good. So this is a little overview. I'll start first with Kolmogorov's now classic definition of what a random variable is, and then it's going to be going into discussing random variables as an algebra, okay? And there's come a little of history there. Then it's about how to represent them, and I said already, I'm saying they're already commuting because this comes up in the history of science really with quantum theory, is that you have non-commuting observations, which are random variables, but you cannot observe both of them at the same time if they don't commute. We'll see that why that happens. Okay, the reason is the uncertainty relation. And I think we're in the right place here because Schrödinger worked on the uncertainty relation as well. Okay, we'll see that. And and I'll make a little think about non-commuting random variables a little bit, because I think this is maybe where computational scientists may get into touch with these things at some point become maybe something where we really compute something with it. Okay, right now they can do little things, but not really something which is meaningful, large computation. Okay, and in between there will be sort of this setup here leads to be able to say what a sample is or observation. Okay. And it leads also to generalized random variables and things like that. Okay, so this is what the talk is about. So the following convention will be used mostly, I think. I don't know whether I was so strict really when I made the slides, but an entity which you can observe or measure, the physicists call that an observable, so I'll take that. Okay, and then the mathematical model of that, also the result of a measurement, we call an observation. Okay. And the mathematical model of an observable, this we will call a random variable, okay? And the mathematical equivalent of an observation, we'll call that a sample. I'll try to keep to that one. I don't know whether they're 100% strict with that, okay? Good. Now, let's go back to Kolmogorov's classical definition of what is a random variable, okay? So if you look at probability theory, it came really late in the history of science that it was put on a rigorous footing. And this was in the 1930s, so almost 90 years ago, more than 90 years ago, sorry. And it builds on the notion of measure, okay? And the notion of measure, of course, was used initially for lengths, volumes, and things like that. Okay, so the primitive objects are a measure space, a sigma algebra of events, and a probability measure, okay? And then the definition of a random variable is that its real valued random variable is a measurable function from this probability space into the reals with the Borel sigma algebra, okay? So that's the definition of a real valued random variable. Good. And of course they commute, okay? When they multiply with each other, they commute with each other. And so once you have a probability measure, of course, you can define what is the expectation, but it's just the integral. And obviously, you see that the expectation is a linear functional. It's also positive, and it's normalized by giving 1 on the identity, okay? And now let's have the first glimpse of what may be a sample. So if you have, let's say, a compact Hausdorff space, which is your probability space, and a nice probability measure, then all continuous functions are measurable, okay? And this here, we want this, the integral we'll see is a continuous functional, okay? So this is what we really want, okay? And on the other hand, if we have something in the dual space, so something which is continuous, the star means the dual space, continuous dual space. If it's positive and normalized, one can prove that there is a radon probability measure such that this is the integral, okay? And the evaluation, of course, for something is continuous, well, it's just applying the delta distribution at that point to the random variable, and it's also linear, continuous, and positive, okay? So this is for continuous random variables, so there is no problem what is a sample. But let's say you widen the space of random variables you're looking at. Let's say you take, to make it just simple, L infinity. So things which don't have to be continuous. But what does it really mean, evaluating the random variable at some point? I mean, it's really a class of functions, not just one. We all know we can change it in 1 point. Now 1 point normally has the measure 0, and it's still the same equivalent random variable. So this doesn't really make so much sense. Okay, you can of course say with Hahn-Banach guarantees there's extensions of this, but there's many extensions. So this doesn't really tell you what it is. Okay. And then another thing which leads to what I want to come to is that Kolmogorov's definition was found not to cover what is necessary in quantum mechanics. Okay. The way Kolmogorov defined things, which was the classical way of looking at things, you have to say is that you can observe all random variables at the same time. This is not true in quantum physics, okay? So you can only observe one set of random variables or observables, but not others, okay? And because they don't commute, this is what came out. In the end, this is the way of formalizing it mathematically, okay? So from this comes another point of view, and it started like 10 years later after Kolmogorov, so in the 1940s, which has random variables expectations as primitive objects, okay? So in the physics language, these are called observables and states, okay? The expectation they call a state, or the state of your knowledge of the state of the world at that point, okay? And incidentally, a similar view, it was there in the beginnings of probability theory. So, and I'll come to that next. Okay, so some of the scientists in the beginning, so this is like 400 years ago, were the Bernoullis, okay, not 350 years ago, something like that, okay? So, and they, of course, they didn't formalize it like that, but if you look at what they did implicitly, they handled it with random variables and averages of random variables, okay? And the rules they used is that they could edit random variables, they could multiply them with numbers, they could multiply them by themselves, they could average them, okay? And constants were also some kind of random variable, one which is not really random. So an extreme case of a random variable. So if you try to translate this into mathematics, then A and B means that they form a vector space. C means that they're an associative and distributive algebra, okay? D means the existence of a positive linear functional, okay? And E means the existence of a unit or identity element in the algebra, okay? So let's put this, look at more into the implicit rules in modern language, okay? So constant random variables, they're always observed with the same value. Every time you observe them, they give you the same value. So they're not really random in this way, okay? So that turns out to mean that there's a unit constant E, such this random variable is just a multiple of this unit constant, okay? And E turns out to be the multiplicative unit in the algebra, okay? So in Kolmogorov's language, this would be the function which is constant to 1 on the whole space, okay? And then the random variables can be ordered. You can say one was positive. Well, it's a positive if it can be written as a square, okay? That's when you call it positive, okay? And then, of course, this gives you an ordering in the normal way, okay? And they also form a lattice, but I will not use this at all. Okay, and the average, the physicists call state, so I'll use this language too here. And it defines the expected value, okay? And it is normalized like this. And of course, you want the expected value of something positive to be positive. A star is, we can see A star. A star is the jewel of my algebra. Okay. In this case, it's the algebraic jewel. Sorry, I didn't make this clear. Here is the algebraic jewel right now. Yeah. Yeah, I should have used a different symbol. Different star. Good. And then observation. So if you observe a random variable with value A and another one with B, you can also observe a linear combination, and it just gives a linear combination of this. And if you observe the product of both, you get the product of the observations. These were the implicit rules they used, okay? And of course, this means here that the observation is also linear functional, and this means that it's a multiplicative on the algebra, okay? And then of course, if you observe the unit, this follows from here, you get always 1. And then if you observe something which is positive, you always get a positive result, every observation, okay? So, and this means that the observations are multiplicative states. So they are states, they satisfy everything which the average satisfies too, but they are also what's called in algebra a homomorphism from the algebra into the algebra of real numbers, okay? So it's called a character, or in physics, it's called a pure state, okay? So, and if we now try to formalize this mathematically, we'll try to capture all these things here, okay? So where are we going? So this is a little preview. So we'll start from a probability algebra. We'll look at representation. So if I write an L, like, so K is some vector space, and this sans serif upright L means all linear mappings, continuous and discontinuous, okay? Because I have no topology at that. And I'll talk about how to put topologies on the algebra and then characterize the states. So these are the possible ways on how you can have an expected value, okay? And of course, we know if you do Bayesian updating, then the expected value changes to the conditional expectation. So this is the change. So it is something which happens on this set, okay? And the characters. So the characters are called the spectrum of the algebra. We'll see why that is in a little while, okay? So this is a hat. And it turns out when we put topology on that, they will live on the unit ball of the dual, okay? And we'll connect this with the spectrum of the random variable, okay? So I'll define spectrum for a random variable now, like you can define in any algebra. Something is in the spectrum if this guy is not invertible in the algebra, okay? So if this was, the algebra was bounded linear mappings, this would give you the normal definition of a spectral value. There's something in the spectrum, okay? And so this is the spectrum of a single thing. We'll talk about the spectrum of the whole algebra later on, okay? And then another question is, how can we compute functions of random variables? That's what we want to do too, okay? And classical random variables commute, but in physics, it turns out you can only observe observables together if they commute, okay? So we'll concentrate on commutative algebra, okay? Because it turns out for non-commutative ones, the characters really is an empty set. So there is no, you can't observe them together. We'll see why that is a little bit later, okay? Good, and the main connection will be the representation of this multiplication algebra L infinity and the multiplicative version of the spectral theorem. So I'll come to that in a second, okay? Good, so just a little bit of algebra for ones who don't remember it. So what is an algebra? I've written it down here. It's a vector space with the multiplication with this bilinear in both things. So this is the distribution law. And it's unital if we have a unit, which is a unit for the multiplication, and you call it commutative if the commutator is 0 for all elements in the algebra, okay? I will not use it, but if you define the commutator like this guy is a Lie algebra. We won't need this here, okay? Now, right away you get one representation, which is called the regular representation. as linear maps on the algebra. The algebra is a vector space, so I can talk about linear maps on the algebra, okay? And this is mapping A into this linear mapping, which just multiply this would be. It's obviously that this is a linear map, okay? So that's an algebra homomorphism, of course, because these guys are an algebra with map concatenation of maps, okay? Now, what is a probability algebra? Okay, so this is an associative unital algebra, okay, and which has a positive linear functional, which is called the state or expectation, and which is normalized like this, okay? And samples will be algebra homomorphisms into the field of numbers, okay? The field of numbers will later turn out to take the complex numbers for that. Okay, so just a few refinements of that now. So observe already the things we looked at already is C, the continuous ones, L infinity, and also all measurable functions, they are algebras, okay? And the integral is a state, and on this guy here, the delta is an algebra homomorphism. So these things exist. I'm not talking about the empty set, okay? And in quantum physics, turns out that the complex structure is really important to describe superposition of states or whatever, so that they work with complex random variables, okay? And then I'm paraphrasing something which Aupin-Levé said and Jacques Hadamard is, they said it much longer, I wouldn't need the whole page, so I'm just focused on the gist is that the shortest path between two truths, real truths, often goes through the complex domain. So that's why I'll take complex algebras, okay? And every real one can be embedded in a complex one. And the nice thing we can add on that is an antilinear involution, which let's say for matrices would be taking the transpose or the conjugate complex and transposed, okay? So it satisfies these rules. Good. So just a few examples of probability algebras, which we've seen already. So continuous ones, L infinity, then L infinity minus, so which is the intersection of all the LPs. So that's the largest algebra in L1, okay? These are all commutative, okay? But then of course, a simple thing, which will come back later for quantum computers, are the complex matrices, n by n matrices with matrix multiplication, okay? And the unit, of course, is the identity matrix. And for instance, this is a possible state. The trace of A divided by N, okay? Because if you put in the identity matrix, you see it's normalized and it has all the other properties that you want. Okay, and the diagonal matrix would be a commutative subalgebra, okay? And observe, if V is an eigenvector of a normal element, then this guy here, the Rayleigh quotient, is a character or a pure state, okay? So this shows you already a connection between these pure states and the spectrum and eigenvectors, okay? Habe ich das verdreht jetzt? Good. Of course, another one which we know already too is if you take a probability space with step functions, okay, then it's simple to define that in algebra there too, so that is an algebra, okay? And the samples, of course, just taking these coefficients of the random variables. Okay, so these are random variables with a finite number of values. Okay, good. So these are just examples. I need a few more things. So of course we can define what are powers. For 0, it's the identity, and this allows me to define polynomials. So that's the first kind of function I can make on my random variables. Okay, well, I can apply that, and we call it element A invertible if there's another element A minus 1, which multiplied with this gives the identity, okay? And then, well, if we start putting topologies on it, we call it a Banach algebra if the thing is a Banach space, and the multiplication is continuous, so it satisfies this here. And we call it a Banach star algebra if I've missed something in between, so we call it a star algebra if the star is continuous. Okay, the star operation is continuous. We call it a C star algebra if this is satisfied here, okay? And then is another notion of a W star for Neumann algebra. And this is if this C star algebra is the dual of another Banach space, Okay, the original definition is different, but this one's easier to understand right at this point. Okay, the main examples is all the linear continuous operators on the Hilbert space. They are the dual of the linear operators of trace class. Okay, and they satisfy all the other stuff. Okay, and then what is a normal self-adjoint or unitary element is the same definition as for matrices, so I don't have to repeat it here. Okay, and self-adjoint elements, which can be written like this, you call them positive. Okay, and the self-adjoint ones are the ones which can really be observed. The others are only there to enrich the algebra. Okay, and the positive elements which satisfy this, they call projections. It would be orthogonal projections if we're in a Hilbert space. Okay, and the spectrum of an element, okay, of course, now is the same thing here again. So this we're already seen this. Okay, and the goal is to first now to see how can we compute functions other than polynomials. Okay, good. Just a little bit now, because I want to describe what the state is. Okay, so if you have a bilinear functional, if you have a linear functional, it defines a sesquilinear form on the algebra just in this way. Okay, so BAC is a sesquilinear form, and of course it defines a linear map. And in case this is Hermitian or whatever, or positive, you say the same thing for this and this here. Okay, and if we have a Hermitian, a strictly positive definite state, let's call the faithful state. So this is here. This one would be not faithful if this would be 0. Okay, so if you want to apply this here, you would have to factor this out. This guy defines an inner product. Okay, and we now get the first topology is we can take the Hilbert space completion of the algebra in this topology, in this norm. Okay. So, and this is called L2 of the algebra with this function. Okay, so this is a definition which works also for non-commuting random variables. Okay, and a representation is an algebra homomorphism, as I said, into the linear operators on some space. Okay, a 1D representation into the complex numbers is called a character, and we already seen the regular representation. Okay, good. So this was just a repetition. So now we go a little bit into topologies and things like that. And so we already seen L2 topology, okay? And I can get another one from the regular representation. So regular representation is a map, okay? And now I concentrate on the ones which are bounded. So I look at this here, okay? And this would be the operator norm of LA of the representation map. And I take the ones where this is finite, and then I carry this backwards, and I define the infinity norm as the operator norm of this representation operator. Okay, and so it turns out that if this gets mapped with a regular representation, of course these are linear maps. So this is a subalgebra of the linear bounded or continuous maps. Okay, and what we can do then, we can take the completion here in the uniform norm. And this we know is a C-star algebra. Okay, so A infinity carrying this backwards is a C-star algebra. Okay, good. And now what are the states? We've seen this already. These are positive Hermitian functionals. So now we want them to be in the continuous dual of this guy later on. Okay, it turns out, so we want to have this and this. We talked about already with this. And for self-adjoint ones, we want this to be real. And of course, we call it faithful if this implies that A is 0. On A infinity now, which is a CR-star algebra, this implies that this here implies that the norm of this is 1 on the dual space. Okay, so it's the states are something on the unit ball in the dual. Okay, this is what comes out here. And you can show then that the set of states is non-empty and is a weak star compact set and also convex. Okay, so it's a flat part of the unit ball of the dual. Okay, the one which is in the positive cone, and so it's the positive cone intersection with this hyperplane here. Okay. Exactly. This comes. This implies this star compact. So, and then this, you can prove for commutative star algebras, that if phi is an extreme point of the set of states, then it's a character or a pure state, then it's multiplicative, and the other way around too. If it's multiplicative, it is an extreme point, okay? But for a general algebra, we don't know whether this set is non-empty, okay? The extreme points, okay? So this is we're going to call the spectrum, okay? The spectrum are all characters or pure states. And on the C-star algebra, one can prove, of course, this is Klein-Millman's theorem, that it's non-empty, the set of extreme points, okay? And it's also closed, so it's also weak star compact. And kernel here is a maximal ideal. And also, Klein-Millman tells you that the closed convex hull in the weak star topology of the set of characters gives you just the states, okay? So you can think of these guys here, sorry, here, the spectrum, you can think it like if you think of C, the continuous functions, then it would be all the deltas, there would be the extreme point, okay? And any integral can be written as a convex combination of weak star limit of deltas, okay? But this is actually what you do when you do Monte Carlo sampling. Good. So then it's easy to see if the guy is unitary, then the spectrum is on the unit circle. If it's self-adjoint, then it's real. If it's positive, then the spectrum is positive. If it's a projection, the spectrum is either 1 or 0, okay? And so we call this the expectation, okay? And this is the knowledge we have how we prepared the experiment or whatever, how we sample or whatever. So this gives you what you expect, what you're going to get, okay? And you can see that the projections can be defined as events. And you can define the probability of an event just as the expected value of that projection, okay? And then this is just to split it into the mean and something which has mean 0, okay? And so this is not so important right now. It's just a geometric picture of what independent and uncorrelated is, okay? So independent is that the two things are here. These are orthogonal, and independent means that the algebras that they generate are orthogonal, okay? See, also, so this means this is the algebra generated by A1 with complex coefficients. So this is what this means here. Okay, like you write in algebra, whatever field times some unknown x or whatever, and then it's the algebra and this unknown. So this is the algebra generated by the element A1, and this twiddle means you've taken away the constants. Okay. Good. So let's see what this means now. So we need a little bit more for our representation to work, okay? So what is the multiplication algebra, okay? So this is, assume we have such a space, and we take as a Hilbert space L2, okay? Then each element in L infinity defines a continuous linear map by just multiplying with that function, okay? So F is mapped into K times F. We call this the multiplication operator, okay? And then turns out that the operator norm is just the infinity norm of this guy, okay? And of course, the adjoint is just taking the conjugate complex here, okay? And so this is an injective C algebra morphism of L infinity into commuting bounded linear maps, okay? And it's called the multiplicator representation. Okay, so I call this mu, okay? And the image of that is called the multiplication algebra, okay? And so it's isometrically isomorphic to L infinity. And one can show that this is a maximal abelian self-adjoint algebra in the algebra of all linear maps, okay? So you cannot enlarge this one without it not being commutative, okay? And this is abbreviated MASA. So MASA means maximal abelian self-adjoint. Okay, self-adjoint is if A is in the algebra, then A star is also in the algebra. Okay? And the continuous ones you call the uniform subalgebra. Okay, good. Now we come to representations. We will show you, we'll get there what a sample is. Okay, so this is called the Gns construction. Okay, you start from a probability algebra with a faithful state. You construct this Hilbert space, which we have already, And then this is the weak star and the weak star algebra. So this is a weak star, W star algebra, L of H. Okay, so these are all linear bounded maps. Then you construct the bounded ones, as we've seen already. Okay, this norm and the C star algebra A infinity, which we've seen. This is the closure in this norm. Okay, and now you can get a regular C star representation. You can map this C star algebra into the continuous linear ones. Okay. And the expectation looks like this here. Okay, so it's just an inner product with E. Okay. And so this, something like this is called a vector state. Okay. So we can represent this here as a C star algebra, subalgebra of the algebra of all continuous linear operators on H. Okay, good. And now we come to the first theorem. This is the Gelfand representations. Okay, so we'll concentrate now on the commutative on a commutative subalgebra. So this is either classical random variables or the ones you can observe at the same time in physics. Okay. So we have a C star algebra B. Okay, and we call the set of characters or pure states, we call this the spectrum of the algebra. Okay, we know it's W star compact. Okay, subspace here. And it turns out that each A, of course, can be viewed as a continuous function of that. And then it turns out that this representation, the Gelfand homomorphism, is actually a one-to-one onto mapping. Okay. So a commutative C star algebra with a state, you can think of it as continuous functions on some compact space. Okay. So that's one of the representations here. Good. So it's what I call this ISO. This is isometrically isomorphic representation in the uniform algebra. And now what? I mean,
so the H, the Hilbert space, is then separable.
The H is separable, yes. It will turn out that it's interesting. And
so you cannot get quasi-periodic functions.
So I'm talking about the simplest version of all this here. So it will work for other things too, but so what you're getting here now is the simplest version of this. Okay, good. So let's see what the spectrum of that is. Okay, and it turns out that the spectrum is just the range of this continuous function. So gamma of A is something in C omega. Okay, so it's just all the values this continuous function takes. So that's the spectrum, and this is what we think of as sample of a continuous function. So we see the spectrum is really, this is what the samples are. Okay, so the first glimpse of that. Okay, and so for a bounded normal A, for instance, we would look now, for instance, on the C star algebra generated from the algebra generated by A and A star. Okay, so it's the closure in the infinity norm of this algebra. Okay, and then there is an isometric representation, if you have such an algebra, onto the continuous functions on the spectrum of this element. Okay, which makes it really nice. So now, of course, I can take, so these are all continuous functions on this here. So now it's easy to take a continuous function of a random variable, because a continuous function of a continuous function is again a continuous function. Okay, so and then if you look at the spectrum of this here, of course, these, so these are all the delta functions. That is the spectrum. Okay, all characters, all pure states look like this. Good. And now we get in the position to define LP spaces and things like this. Okay, so we could define what I said already before, a continuous function of a random variable. This is the continuous operational function. Calculus, sorry, so this formally written down is this. It means just a continuous function of a continuous function. Okay, and if this is real valued, then this random variable is self-adjoint. If the norm is 1, then it's unitary and so on, the things you would think of. Okay, and so we can also now define for non-abelian algebras. This way we can define continuous functions of normal elements. Okay, good. And which means this also, the absolute value is a continuous function. Okay, so in this way I can define what the square root of a continuous element is, of a positive element is, okay? So it's the absolute value of this guy here, which tells me that it's positive. And having the absolute value, I can look at this here, and of course this is the P norm, and I take the completion in this P norm, and I get all the LP spaces, okay? And my L infinity minus, so the largest algebra in L0. L0 can be get a topology with a metric D here, okay? And this would be the metric, the expected value of this here. And that this is a complete metric space, but not locally convex, unfortunately, with this metric. Okay, so you get all this classical spaces this way. Good. A little bit more work has to be done for L infinity, because if I take the continuous functions, they're already closed in the uniform norm. So if I take a uniform closure, it's the same space. I have to transport back from this is what this says here. I'll make it just in a few words. I have to transport back from the regular representation. I have to transport back the weak operator topology. And in this topology, I can take the closure of my algebra, okay? And so this gives me, if I do this for the continuous functions, this gives me L infinity. So I apply the same procedure now on my C star algebra, and I get this way L infinity, okay? So L infinity is the closure in this topology, which comes from the weak operator topology, okay? And it's a W star algebra. Good, so now we have all LP spaces. Good, and this tells me I can do the Borel spectral calculus. So this is what you do for operators too, of course. You can say, first of all, we get from the function. So we have a positive normalized functional on the continuous function. Of course, this gives me a radon probability measure on the spectrum, okay? And the question now, what is the spectrum or a possible sample which something which is in L infinity? So I come to this question now, what is a sample? So from what I told you before, a sample is something which is in the spectrum, okay? So something where this guy is not in L infinity. And this can be rewritten. Those are the complex numbers, which is called the essential range, okay? Something that the push forward measure of every neighborhood of Z is larger than 0, okay? So this is called the essential range or the spectrum of an L infinity function. These are possible samples of an L infinity function, okay? And then you can extend this to the unbounded ones as well, okay? And then you can define now functions. So if you take any LP function on sigma A, you can define this as a limit of a net converging in the appropriate topology. And this gives you the bounded Borel operational calculus on linear mappings, and this way also on the algebra. Okay, so I can apply now any measurable function to a random variable, and it's still a random variable. Good. Now, because we are at the Erwin Schrödinger Institute, and he has something to do with uncertainty relations, just put this in here, okay? So let's say you have a self-adjoint random variable, okay? And then you define what is its uncertainty. Well, again, this is the varying part. The uncertainty is just the expected value of this guy squared, okay? So it's something like the variance, this uncertainty, okay? And of course, it is this here. So from this, you get also this here, okay? Now, if this guy here is multiplicative, okay? So which means it's a character or a pure state, okay? Then, of course, it gives you this here. So the uncertainty of pure states is 0, which means you can observe them exactly, okay? So there's no uncertainty with pure states. So an observation or sampling without uncertainty is possible, okay? And now let's look at the combined uncertainty of two self-adjoint things, A and B, okay? So we'll multiply the uncertainties by this here, this is this times this, and then by Cauchy-Schwarz, this is this here, okay? And be losing this thing here. Okay, so this is just a complex number, okay? And then of course, its modulus squared is just the real part squared and the imaginary part squared, okay? I'm just going to look at the imaginary part. This will give us the Heisenberg uncertainty relation, or what's called the Robertson uncertainty relation. If you look at the real part as well, you get another uncertainty relation, which is a bit sharper and which was actually done by Erwin Schrödinger. So, but that is a little bit longer, so I'll just look at this one. So let's look at the imaginary part squared, okay? And of course, this can be written like this, 1 over 2i, the difference of z minus z bar, okay, which is this. And then I just insert what this is. Z bar is just with the two things exchanged, okay? And I rewrite this again, what this is here, and this is this. And so in the end, I can get out. So this is phi of the commutator, okay? So now the last thing to do is to take the square roots, and we got this uncertainty relation, okay? So the uncertainty of A times the uncertainty of B is always larger than the expected value of the commutator, okay? Which tells you if two things don't commute, you can't get them both observed with no uncertainty, okay? So this is the basis for Heisenberg's uncertainty relation. You have to be a bit more careful. I did it here for bounded things. All the operators Heisenberg dealt with are unbounded ones, and then you have to be a little careful what you do when they commute, whatever that means. But it can be done there too, okay? So we have a lower limit of uncertainty for non-commuting random variables. This is what this gives, okay? And generally, a sampling of non-commuting random variables is not possible, okay? The spectrum is empty then. It's not commuting, okay? Good, so where have we come to? So I hope I've shown you in this very sketchy way how to formalize the idea of possibly non-commuting observables as a probability algebra, and that the representations of these probability algebra play a very vital role. The key was the regular representation, okay? The observations turned out to be samples. And Kolmogorov's classical definition turns out to be just one way of representing this algebra, okay? So it is just one representation, which in my view maybe opens, so we'll come to this question, so is maybe, are there other representations when you compute, which may be better for what way you're computing and things like that, okay? So now every abelian C-star probability algebra looks like the continuous functions on a compact set, okay? And every weak star, the W star algebra closure looks like L infinity. And it's a maximal abelian Salver-joint algebra, okay? So you cannot add any more observables which can be observed at the same time. Okay? And the samples appear now as continuous characters, okay? And we can compute functions via operational calculus. So this is how far we are now. And so which topologies have we used? So we can define LP for all P between 0 and infinity, okay? Now we can identify the unbounded A's. Remember, I just looked at the bounded ones first. So the unbounded A's are a subalgebra of this guy here. Okay. And for abelian algebras, you can represent the multiplication by a possibly unbounded function of multiplication by possibly unbounded function. Okay. So we got this system of algebras. So AB. This is its completion. This is a closed subspace in here. And of course, this sits in the algebra and the algebra sits in here. And of course, this sits in this algebra here of all measurable guys, okay? Good, and similarly, we have sort of Banach-Gelfand triples, okay? When we look at this, so a L infinity is continuously embedded in LP for P between 2 and infinity, which is continuously embedded in L2. This I take as a pivot space and identify it with its dual or anti-dual to make it really exact. And this sits in LP star, and of course this sits in L1, okay? And this is the pivot space here. So this comes, and the pivot space, remember the L2 comes from the expectation. Good, so now some questions to the audience. So this is a talk where I can ask questions and you give me the answers afterwards, okay? So one question for me comes up here, is there other representations than just measurable functions? okay, which may be helpful to understand certain aspects or for specific numeric computations, okay. And so we've seen the regular representation and the function algebra representation, okay. And for samples, we've seen the character or pure states representation. So the question still is now how to sample things which are, say, measurable functions but are not continuous. We know we have to look at the spectrum. We have to find the spectrum of this thing, okay. And the other thing which comes up here now, we've put this functional analysis point of view here is there a good regularity theory possible for solutions of stochastic equations? I know there's a little bit starts, but if you look at the regularity theory of PDEs, I think for stochastic PDEs, for instance, we're still at the very, very beginning. So, I mean, so a stochastic PDE transforms some random fields into another random field, okay? And the question is, if the input has certain regularity, what does this mean for the output? So that's a question, I think, which should be addressed because if you have a good space where you can identify your thing, then maybe you need fewer samples to approximate whatever you'd like to do, okay? And the other thing which this offers is to deal with wild random variables, I'd say, okay? Things which are not measurable functions or generalized random variables, okay? So look at, for instance, generalized functions in normal analysis, okay? So they are defined as the dual of something very smooth in some certain topology, okay? But they cannot be represented as functions. But as Dirac said, it turns out very helpful to have them, okay? And for Neumann said, this formulation is unsurpassed in elegance, but not possible to justify rigorously mathematically, which was wrong because it happened a little bit later on by Sobolev and Schwartz. Yeah. Good. But we would like to have some things like this, for instance, white noise. What is white noise? What is Donska's delta? This is a delta function where the argument is not a point in space, but a random variable. A very strange random variable, but something people like to have. Good. So now let's come back to sampling. This is just a few ideas on how you can sample things which are not a continuous function, okay? So for continuous things which can be represented as a continuous function is clear, but what to do for the ones who are not? And we'll start first to look at the bounded ones, okay? So it's just by cutting it off at some number n, so you can deal always with the unbounded ones in terms of the bounded ones, okay? So if you want to have something as value which is between minus n and n, then you look at this function, okay? So that's in infinity, but the problem is that to look at the dual of n infinity is not very easy to see what things look like that, okay? So, and so there will be one way to go is via the regular representation. We know all these things can be represented as linear maps, okay? But they may be, if like here, they may be possibly unbounded linear maps, but they're densely defined self-adjoint operators, it turns out. All of them are densely defined self-adjoint operators, actually defined on the same domain, okay? So sampling, therefore, is equivalent with computing spectral values of a linear, possibly unbounded operator, okay? Just to remind you, one way of doing it, I suppose everyone knows this. So this is the spectral theorem for matrices. There's three versions which I want to look at. The multiplicative one, which tells you can compute functions like this. The one with projections, which means A can be written like this here, A applied to some vector V, okay? And functions, of course, look like this. And there's a formulation in eigenvectors, okay? So AV looks like this here, okay? And F of A looks like this here. Of course, in finite dimensions, they're all equivalent, but in infinite dimensions, they are not, and they require a little bit of work, especially the last one. So the first one we actually seen already, this was the multiplicative spectral theorem. Okay, we've seen that any commutative algebra, let's take a self-adjoint operator, okay, and we look at the C-star algebra generated by it. Well, when we have our Gelfand representation, it tells us this looks like a continuous function. So this is the multiplication version, okay? So it means there's a unitary U here, and I can write A like this, where this is a multiplication by the identity, actually, okay? So I can make it the measure space. So A is like the multiplication by identity, okay? And functions, measurable functions, well, they will be in the W star algebra, which comes from it, okay? And the other one is the ones most people know. This is the projection measure spectral theorem, okay? If you take something in the spectrum, we define these projections here in L infinity. We take these, so this is just 1 up to lambda from minus infinity. And then these projections will be just this applied to the operator. So that's an L infinity function applied to the operator. I can do this with spectral calculus, and it turns out to be a projection, okay? And then A can be written like this, and f of A, of course, can be written like this. So this is the one spectral theorem most people know, okay? If I now go back to random variables, okay, then this guy here, actually, the expected value of that turns out to be the distribution function, okay? So and then everyone knows that you can kind of write the random variables here, and of course, this is known by everyone, so this is the normal definition of the expected value, okay? Good. To get at the last one, and I think that's something which is quite interesting to look at for several reasons, you need a little bit of theory, okay? So imagine we have a space F, so what I want to talk about countably Hilbert spaces and nuclear spaces for a second, for the ones who don't know it. Just a quick review, okay? Imagine we have a sequence of norms which are ordered like this, okay? And we take Vn, the closures of this space here, in this apparent norm, and the dual space we call V minus n, okay? Then one has these dense embeddings here, okay? Again, identify this with 0, that's a Hilbert space. I identify this Hilbert space with its dual or anti-dual if it's complex here, and then it goes on like this. And then I can form these spaces here. So the intersection of all the VKs, and that's what's called a countably Hilbert space. And I put the topology of the projective limit onto the space. So it's a locally convex space, and the family of semi-norms is all these norms. Okay, so that's what the space looks like. And it turns out to be a complete Fréchet space. Okay, and its dual here is an inductive, injective limit, sorry. Okay, and all these spaces are separable. Now, if one of these injections here, so if always, or some, for all n, you can find a larger m so that this injection is nuclear, then this space here is a nuclear space, okay? Call it a nuclear space. They're nice because on joules of nuclear spaces, you can define measures, okay? We all know of the difficulty of defining measures in Hilbert spaces or Banach spaces or whatever. It turns out it's simple if your space is the joule of a nuclear space, okay? Good, and now, often these norms here come from a linear operator. Let's say we have a densely defined, essentially self-adjoint operator. We can define the norms just as the sum of the powers of x, okay? And then it turns out when I do this construction that A is a continuous map here, okay, on this space, and AK is a continuous map from here to here, okay? So, and in case V is not nuclear, it's possible to find a nuclear U where it continues on that one, and we have this embedding. This is called a nuclear Gelfand triple, or a rigged Hilbert space. Rigged like because it's been rigged up with these U's left and right. Okay, it doesn't mean that it's something wrong or something like that. Okay, good. And this allows me to formulate the spectral theorem in eigenvectors. How are we doing with time? No. A little bit left. Okay, so in this rigged Hilbert space, it's possible to define A, how it operates on U star, okay, and then you can find generalized eigenvectors, so you can find elements in U star, which looks like this, okay, so V, oh no, the epsilon here, it comes from here, so I can apply U for that, okay, and this I define to be this here, okay, and you can find U lambda so that this is true, okay. So in a case it's in H, then it's a usual eigenvector, and otherwise it's called a generalized eigenvector. And it turns out for self-adjoint operators, you can show for each lambda in the spectrum, there is a generalized eigenvector. Okay? We've seen before from the eigenvectors, we can define the pure states, and maybe this is a way to, and the pure state will give me the spectral value, which is that lambda. Okay? Good. So, and it turns out that it's possible to define a measure on the spectrum, okay, and a measurable map here into these U lambdas, such that for all things in the nuclear space, we have this here, Okay, so this is the one in eigenvectors we had before with the sum. The sum has now turned into an integral because, of course, the operator can have a continuous spectrum, which is not possible in finite dimensional spaces. Okay, just a recall of what types of spectra we have. Okay, so of course, this is the normal definition of a spectrum of a linear operator. And so these guys are called the point spectrum when you have really an eigenvalue where the kernel of this is not equal to 0. Okay, so really have an eigenvector. Okay, and the rest is called the continuous spectrum. And the eigenvalues which are isolated and have finite dimensional eigenspaces, they're called the simple spectrum. Okay, some people have other slightly definitions with the same names, but unfortunately there is no unified version of this. And the rest is called the essential spectrum. And it's two things which are already known or been proved by von Neumann is that the essential spectrum is stable under perturbation. So if you add a compact self-adjoint C, then it doesn't change the essential spectrum, okay? And on the other hand, continuous spectrum or this one is not really stable because you have an A here, okay? You can add a little C with arbitrarily small norm such that the continuous spectrum is empty and all the spectrum is point spectrum. So, but they're possibly not isolated and eigenvalues of infinite geometric multiplicity. Okay, good. So now how do we sample the spectrum? Okay, so for the simple spectrum, there's an eigenvector, and then this is a pure state. And for the other ones, it will only possible, in my view, to get smooth approximations to it. Okay, and we've seen for something like this here, there is a normalized eigenvector. So this is an infinite dimensional one. So this would be still a pure state. You have to find this in an infinite dimensional space. But in the continuous spectrum, there is no eigenvectors. This is what it means to be in the continuous spectrum. But we know there's generalized eigenvectors. So if you can't find them and a V so that this is non-zero, you can compute this guy here, and this would be a pure state for that. Okay. Another way of sampling the spectrum is just to say, if something is in the essential spectrum, we know there's an orthonormal sequence of vectors such that this here converges to the lambda to the value on your state. Okay, so that would be another way of doing it if you can find this here. Okay, other calculations are based on the resolvent. Okay, so on the probability algebra, this would look like this. Okay, and we know that this is bounded if the imaginary part of Z is non-zero, okay, for self-adjoint A's, okay? And we know that this guy here has a jump across the real axis, okay? So if you look at this here and you let epsilon go to 0, if lambda is in the spectrum, there's a jump, okay? So therefore, you can take this now for random variables and look at this function here, okay? And if this has a jump, so if this is the jump here, and if the jump is non-zero, then lambda is in the continuous spectrum. Okay, this is one way of computing it. It gives you so of course you can only compute this for finite epsilons. It'll give you a smooth version of what the spectrum is. Okay, so all these things would be possible values. So this would be my answer now. I'll ask you later what you think is a sample. This would be my answer. What is this sample? Something which cannot be represented as a continuous function. Okay. And now, just let me go to this question of regularity for the 2 minutes I have left. We all know polynomial chaos expansion, okay? So, and these are the usual Hermite polynomials, okay? And we know that this is the closure of the direct sum of all these homogeneous chaoses, okay? And any F now can be written like this, okay? And the norm looks like this because this is the norm squared of these guys. Good. And now I can define, and this is my proposal for looking at regularity to look at these spaces. These are spaces used in what's called white noise analysis or stochastic analysis, okay? So for some F and H, we define some operators for rho between 0 and 1 and K a natural number. A rho K is just taking this guy as an eigenfunction, and this is the eigenvalue, okay? And where this guy is this here. From that, I can define these Hilbert norms, okay? This, of course, is positive, so this is a positive operator here. And this gives a separate Hilbert spaces, these guys here, separate Hilbert spaces where this is lesser infinity, okay? And the duals, I call the ones with minus k. And these are the Hida-Kondachev spaces, okay? And again, I can do the same construction I showed you before, okay, for a nuclear space. So I can construct this thing. This guy is a nuclear space and nuclear Fréchet space, and this is its dual. Okay, so these are very smooth in some way, random variables, and these are generalized random variables which can topically not represented. And I'll be finished in a second. Okay, good. So these are already there in the literature, and then you get this kind of embeddings between these test spaces and distribution spaces. Okay, one thing maybe which is interesting for sampling is similar thing can be done by defining the number operator, okay, which just takes this times n. N is the length of alpha, okay, and we look at these norms, and this gives you the equivalent of Sobolev spaces now for random variables, okay, spaces of random variables which can be k times Malevich differentiated. Okay, for p equals 2, of course, they're Hilbert spaces, and we get again these kind of embeddings. Okay, and the interesting thing, for instance, you can show if f is in this space here plus something else, which I haven't written down, then it can have a density. Okay, so that may be an interesting thing to know whether your random variable actually has a density or not. Okay, and if it's in this guy here, then it can have a smooth density, actually. So the density would be infinitely smooth. Good. Just a little glimpse of quantum computing where this comes, the non-commutative ones. So just give me one more minute, if I may. What is a qubit is something in C2. So typical basis vectors are 0 and 1. This is written in the ket notation of Dirac. Okay, so 0 is, the qubit is 0, the 1 is 1. Okay, so this spans the space. And n qubits are represented by the tensor product of this n times, okay? What is a quantum computation? You take an input, and then there's a unitary transformation, which gives it an output. So then your physical device is in some state A. And now you have to observe the state. This is getting the result of the computation, okay? And now we come to where we are, okay? So if you want to measure it, we want to determine which qubit is in which state, okay? So we have to do measurements. Of course, so measurements on this here, we know have to be self-adjoint things in the algebra on this Qn here, okay? But they're not without error, and they're not commutative, okay? So we have to take a commutative set. These things can be observed at the same time, okay? And the expectation, of course, is given by a state, and typically the states look like this, with R being the density matrix which satisfies this here, okay? And the observations you get are something like this. So this is an error which you have. Typically in a quantum computation, you have to do the computation many times and average the thing. Okay, so you have to do statistics on the result. So instead of this, you observe this here, and hopefully the expected value of the error is 0. So you have to perform many, you could say, Monte Carlo samples to get the results. The error is small enough. So that brings me to my conclusion. So I've shown you that probability algebras and even for non-commuting random variables are possible and actually give you probability theory without measures. In some way, the measure comes out as a secondary thing. Expectation operator and random variables are central objects. They have strong connections with spectral theory and functional calculus. Sampling in this view is the same as determination of a spectral value. And the duality theory allows wild random variables and may be one way of characterize regularity of random variables. And this is a simple non-commutative example. So thank you very much for your attention.